And then we'll get into section 7.12 and wrap up the chapter. Hi there, Chemistry 3101. This is where we left off last class, was talking about section 7.11, which is called synthetic strategies and the overview of synthetic strategies. And if you're wondering, first of all, why do I have to learn all these different reactions in organic chemistry? You taught me so many different reactions. What's the point? Well, the whole point is what I have highlighted here in yellow. It's to make valuable, complex compounds from cheap and readily available starting materials. So we want to take something that doesn't cost a lot of money, and we want to make something that does cost a lot of money. And a lot of times what we want to make, and something that I'm interested in, and the author of our textbook is interested in, is creating new medicines that can extend and enhance human lives. And so if you look at any prescription medication, or not any, but a lot of prescription medications are small organic molecules, and it requires organic chemists to be able to find a way to make those molecules. And thus, organic chemists have to know a whole holy host of reactions like these ones here. If you have a primary alkyl halide, we can do elimination reactions. We can do substitution reactions. We can make new functional groups. We can make alcohols, alkenes, ethers, thiols, esters, nitriles, right? We can do a whole bunch of different things to make make new functional groups. And again, if you look at marketed drugs, prescription medications, you'll see many different functional groups represented in pharmaceuticals. Also, we talked about tertiary substrates, and we said, well, similarly, we can do substitution reactions with a tertiary substrate. We can do elimination reactions. We talked about the Zaitsev product, the Hoffman product, and hopefully you went over that over the weekend and get some practice on that. And so once you put all of these reactions together, it's a lot to put in your mind. It's a lot to remember. How do you put all this stuff together? Well, something that you can do sometimes is use something called retrosynthesis. And we're going to take a look at retrosynthesis. It says when thinking about how to make something, sometimes we just look at the finished product first. You start with the finished product and you say, okay, well, what is the reaction that I would need to make this product? I might not know how to start from my reactant, from my starting material, but I know I could use this reaction to make, the final product. And then you can kind of go backwards, right? What it's saying is that first we look at the desired product and figure out, backwards, how could we make that? And we call that retrosynthetic analysis. It is very handy. Now, I'll be honest with you, at this level of organic chemistry 1, many students will just be able to solve problems a lot of times, and this applies to every student. A lot of times you'll just look at a reaction and say, okay, I know how to get from A to B. I can do that. But sometimes you might get stumped and you say, okay, well, then I'm going to have to try a retrosynthetic analysis. Let's say you wanted to make this ether. Right? You want to make this ether. Well, how could you make that ether? What you want to do is identify a bond in that molecule that you would know how to make. And let's say if you were to break this bond right here, and that's the one that's shown here, they just have it drawn a little bit differently. But let's say you broke this bond. I mean, how would you make that? We have 1, 2, 3, 4, 5 carbons on this side, and then we have an ethoxy group over here, an ethyl with an oxygen attached to it. We call that an ethoxy. Well, how could you make that? You could make that from an SN2 reaction between a primary alkyl halide, like 1-bromopentane, and sodium ethoxide, right? It's just going to do a regular old SN2 nucleophilic attack, loss of leaving group simultaneously. So what you're doing is you're kind of thinking backwards, what would I use to make that compound? Now, another option would be to break the other side of the ether. What if I had this alkoxide over here, and what if I just had ethyl bromide? Would that work? Absolutely, that would work. There's nothing wrong with that answer either. And so what you're going to see is not all of the time, but many times in organic chemistry, we'll have more than one way to make an organic molecule. We'll be able to make it a couple of different ways, and they'll both be correct. So there we go. You'll find that when you're thinking backwards, oftentimes you're going to come up with more than one way to make a target compound. And so here's a proposal. Let's say we take the alkyl bromide, this one, we treat it with sodium ethoxide. So this is the same thing as NaOET that we use all the time. Oops. fix that up a little bit. There we go. Okay, in DMSO. And it says we're going to choose an aprotic solvent. Now, this is something I'm going to address in section 7.12, why you would use DMSO and what DMSO is. So just hold tight and we'll go over that. Now, let's look at another example. Let's say you wanted to make this compound here. Now, this is an ester. It says, what reactants would you need to make this compound from a substitution reaction? Well, if you go back, let's go all the way back to where we started this morning. And I said, well, how would you make an ester like this one here? What you can do is you can take a primary alkyl halide, and then you can do a substitution reaction with the conjugate base of the carboxylic acid, Now, this is called an acetate ion. And so if you're still looking at me going, what are you talking about, Mr. Dion? Hold on, let's go back and I'll show you. So if we go back here to this ester, what I'm saying is that we could break this bond. So let me use my green pen or my red pen. Let's say we broke this bond here. Then what would we have? What we would have would be this acetate ion, which is a nucleophile. And then we could use 1,2 carbons with a bromine on it, so bromoethane. And we combine those two. And what's going to happen is we're going to get a nucleophilic attack and a loss of leaving group. And we're going to end up with this compound. So you see what I'm doing? I'm kind of thinking backwards. You know, how would I make this molecule via a substitution reaction? So with all that in mind, let's take a look at a quick question here. This isn't a really laborious one, but it just says, for each case below, transform the given starting material into the desired product. Okay, and more than one step may be required. In order to plan a reasonable synthesis, it might be a good idea to start with a retrosynthetic analysis of the target molecule. Well, personally, I think that some of these do require a retrosynthesis, maybe. Other ones, excuse me, not so much. Well, let's take a look at A, and I'm going to redraw this secondary alkyl halide, this one here. So I've got a red beta proton here, and I have a blue beta proton here. Remember, the carbon that the halogen is attached to, that's the alpha carbon. Anything branching off from it, any carbon attached to it would be the beta carbon. I guess I should color code these a little better. Huh? I'll put a blue here and a red here. So I have two different types of beta protons. I can pull off the red proton, and what that would make would be this compound. So I'd end up with this compound if I pulled off the red proton. But if I pull off the blue proton, then I end up with the desired product. Well, my question to you is this morning, could anybody tell me, would the blue product be called the Zaitsev product or the Hoffman product? And it's not a trick question. Would blue be Zaitsev, because that's what we want, or would it be Hoffman? Absolutely, Clinton. It's the Hoffman. Thank you, Kiana. Perfect. Absolutely. So this is the Hoffman product. And if we want to make the Hoffman product, who can answer me? What would I want to use? Would I use a hindered base or an unhindered base? Hindered base or unhindered base if I want to make the Hoffman? Exactly. Yes, 100%. My students are all crushing it. And the answer is you'd want to use a hindered base to make the Hoffman product. Now, if you wanted to make the Hoffman, what would be a good hindered base? Potassium 2-butoxide is a great hindered base for that reaction. But if I wanted to make the Zaitsev product, let's say I wanted to make the Zaitsev product, and I don't, but let's just imagine I did. Well, if I want to make the Zaitsev product, could anybody suggest a base to make the Zaitsev product? I kind of just noticed that we're solving B, aren't we, at the same time? So this is A, and this is B. Anybody could suggest a base to make the Zaitsev product? What's an unhindered base that would work well? Anybody? We knew that T-butoxide was a hindered base. Let me refresh my chat just in case I'm missing something. Okay, so an unhindered base, exactly. Okay, I see my students are getting it. Right on. Yeah, so you'd want to use something like ethoxide or methoxide. So you could put sodium ethoxide. Kiana, you could put sodium methoxide. Either of those are going to work. Since Kiana wrote ethoxide, I'm just going to delete that one, just have one reactant or one reagent. There we go. So now we've solved A and B. And the last one, I'll just kind of go over it with you quickly. I mean, there's a few ways that you could do C. Okay, I see that there's two ways to do C. One way would be to convert the alcohol into a good leaving group by converting it into a tosylate. That's one possibility, but there is another option. Okay, if you were to convert the alcohol into a tosylate, so let's say you use tosyl chloride and pyridine, then you end up with this compound. So let me just scribble it in. And now you've made a good leaving group. Now you've got two types of beta protons. You've got the red beta protons and you've got the blue beta protons. Well, the red beta protons are the more hindered protons. And therefore, if you used an unhindered base like sodium ethoxide, that would give you the desired product. Okay, that would totally work. Could anybody tell me, is there another way to do this reaction? And I'm talking about this one right here. Is there a simpler way to do this? Because this one is 2 steps. There is another way. So if we have an alcohol, we can treat that with a strong acid like sulfuric acid. And when you do that, if you treat this alcohol with sulfuric acid, what it's going to do is it's going to protonate the alcohol to convert this into a good leaving group, which can then leave. Okay, and once that leaves, it can undergo an elimination to make the most stable alkene. And so the conditions that we use to do that would just be sulfuric acid and heat, because when we do that, we always end up with the Zaitsev product. Zaitsev product, which is what we want. This is the Zaitsev product. And so either of these ways would work. If you were studying with a friend and your friend put, you know what, I say what you do is step 1, tosyl chloride and pyridine. Step 2, sodium ethoxide. I would give your friend 100%. And if you said, I think I would just use sulfuric acid and heat it up, and that's going to give me the Zaitsev alkene from this secondary alcohol, I would say that's perfectly reasonable too. I'd give that 100% as well. Again, 2 different answers, both completely correct. Now, before you run away with that and say, oh boy, for everything there's going to be multiple answers, it's not always the case, but a lot of times it can be. And you can imagine that as we progress through the course and we learn more and more and more reagents, you'll find more and more ways of making compounds. And that's even, we see that to an even greater extent in organic chemistry too. All right, let's do something different. So before we left for the weekend last week, I asked you to read the last 2 sections of chapter 7. So I'm going to assume that you all read section 7.12. There's quite a bit of information in there, but I'm going to try to summarize it as quickly as I can. It says, if you're doing an SN2 reaction, an SN2 versus an SN1, for an SN2 reaction, it says the best solvent to run an SN2 reaction in is a polar aprotic solvent. So notice that the polar aprotic solvents are these over here. Now, if you're wondering, you know, what are these exactly? Okay, so when you're running a reaction, okay, so let me just draw a flask here. So let's say you have a flask like this, and you have your organic molecules in there. Well, you've got to have it dissolved in some kind of medium, right? It's got to be dissolved in some kind of liquid and then stirring, right? Most reactions in chemistry are done in the liquid phase. Now, in general chemistry, in chemistry 1401 and 1411, if you took them at UCCS, almost everything that you did, in fact, probably everything you ever looked at was in water. But in organic chemistry, we run very few reactions in water. So we need solvents. Here are some of the common solvents. Well, looky. The first one is water. Anyhow, so what are some solvents we could use? Well, protic solvents would be things like water, methanol, which is wood alcohol. Don't drink it. It can get you intoxicated, but it can also kill you and make you go blind before you die. Anyhow, ethanol, which is the same ethanol that's found in Coors Light. Then we have ammonia. Ammonia is found in things like household cleaners like Windex. And then acetic acid. Now notice what is in common with these protic solvents is that they all have a hydrogen attached to an electronegative element, whether it's an oxygen, okay, or a nitrogen. So that's what all of those have in common. So we call those polar protic solvents. So you could write in here, besides protic, technically you could call these all polar products because they are all polar. But anyhow, we could call them product solvents. And you probably noticed that the aprotic solvents, they all have hydrogen atoms in them, right? Like let's just take acetone, for example. Acetone is nail polish remover. Anyhow, acetone has 6 hydrogens. There's 3 here, there's 3 more here, but none of those hydrogens are attached to an electronegative element, okay? So again, I repeat, in all of these solvents, there's hydrogens, but none of them are attached to a nitrogen or an oxygen or anything like that. So what are these polar aprotic solvents? So acetone, you can buy that at Home Depot in the paint section. You can use it as a paint remover. It's nail polish remover as well. This one here is DMSO, dimethyl sulfoxide. You saw it a few slides ago. Dimethyl sulfoxide has a pretty high boiling point, and it gets absorbed through your skin very easily. So it's one of those things you want to handle with care. What next? DMF, dimethyl formamide. So DMF is another great polar aprotic solvent. Again, you can see a hydrogen, and there's 6 more hydrogens here, but none of them are attached to the nitrogen or the oxygen. Acetonitrile is another one, and this one here, which I've only used a few times in my life, is hexamethylphosphoramide, or HMPA. It's a very difficult solvent to work with because it always has to be stilled freshly before you run a reaction with it. So HMPA. Anyhow, so we've got all these polar aprotic solvents. Again, they're all polar. They all have dipoles in them, right? This has a dipole. This has a dipole. This has a dipole, right? There's a dipole here. There's a dipole here. But none of them have a hydrogen attached to a electronegative element. So why is it that SN2 reactions work best in these kind of solvents? Well, check it out. It says that protic solvents can engage in hydrogen bonding and stabilize anionic species like a good nucleophile. So let's imagine you have a good nucleophile like iodide. Okay, iodide is a really great nucleophile. Well, iodide is negative, as are most strong nucleophiles. So what's going to happen if you have a water molecule? Well, water, or any of these polar molecules, polar protic solvents, is going to have a delta negative on the electronegative element, but all those hydrogens have a delta plus. So what it does is it stabilizes that negative charge. You don't want the negative charge stabilized if you want it to perform a nucleophilic attack. You want it to be destabilized. And so protic solvents can stabilize the nucleophile, and so they don't work well for SN2 reactions. Now, if you're saying, well, hold on, Mr. Dion, acetone has a dipole in it, but hold the phone. Let's check it out. If we look at the dipole of acetone, so let me just I'll rewrite the iodide over here. Oops, where's my pen? There we go. Let's rewrite the iodide here. And you might say, well, come on, there's a dipole in acetone, right? We know that there's a dipole going in this direction. So the oxygen is delta negative and the carbon is delta plus. But the thing is, if you look at any of the delta pluses in any polar aprotic solvent, is that it's blocked, or they're always flanked by something that prevents any kind of stabilization. So there's no stabilization, which lets the nucleophile run wild. Okay, it just lets it do its thing. So it's ready to just perform a nucleophilic attack. So there we go. Now going back to yeah, that's enough of that, I guess. So here's a kind of a graphical representation of how a polar aprotic solvent enhances the reaction rate for an SN2 reaction. So this is DMSO right here. So DMSO is this, it's dimethyl sulfoxide, this thing here. Okay, I'm just redrawing it. That's what they have here. I'm just going to put in all the lone pairs now. Okay, so what they're saying is that if you're in a polar aprotic solvent, just like with acetone, yes, you have the delta negative here on the oxygen, but the delta positive on the sulfur is too hindered by those 2 methyl groups to stabilize the negative charge. And what that does is it raises the energy of the nucleophile. So in a protic solvent, your nucleophile is going to be stabilized, whereas in an aprotic solvent, it's going to be destabilized. So the rule of thumb that I want you to remember moving forward is that if we want to do an SN2 reaction, we want to use a polar aprotic solvent. Whereas if we're doing an SN1 reaction, we want to use a polar protic solvent. Okay, that is the rule of thumb that you need to know in this class. Polar protic solvents are best for SN1 and polar aprotic are best for SN2. It doesn't mean that you can't do an SN2 reaction in a polar protic solvent. It just means they're best in a polar aprotic solvent. So again, something I want you to think of moving forward. And with that in mind, let's take a look at one last question from these slides and see if we can solve this. You can see I copied and pasted this directly out of the textbook. Question 7.42. Here we go. Which of the following reactions is expected to produce one propanol at a faster rate? So let's investigate. Both of them have the same substrate. So it's 1-chloropropane. Both of them have sodium hydroxide. It's a strong nucleophile. It's also a strong base, but they're only drawing the product of the SN2 reaction. And here are our solvents. We have water, which is polar protic, and we have DMSO, which is polar aprotic. So right here, polar protic, or you could just write protic if you want. And DMSO is polar aprotic. Who could tell me which one of these reactions would occur at a faster rate? Would it be the one in water or the one in DMSO, based on what we saw in that table? Exactly. So this one is going to occur at the faster rate, the one with the polar aprotic solvent. So faster, and this one is going to be slower. All right. Let's look at the next one. It says, which of the following reactions is expected to exhibit a faster rate? So again, we're talking about the rate of reaction. We're using ethyl bromide. We're using sodium iodide versus sodium chloride, and they're both in the same solvent, ethanol. So what's happening here is just an SN2 reaction. Okay, so we're doing an SN2 reaction. The solvent is not what we're looking at here. The difference between the two is the nucleophile. Right, we have iodide and we have chloride. Could anybody tell me which would be a better nucleophile? We know that iodide and chloride are both good nucleophiles, but could anybody tell me which one of these would be a better nucleophile? Which one do you think would be a better nucleophile? So I see I have a few different answers, but the answer is going to be the iodide. This one will be faster, and this one is going to be slower. Why is that? It's because iodide is a better nucleophile. So we'll put here iodide is stronger nucleophile than Cl minus. Now they're both halides. They both have a -1 charge. Why would iodide be stronger? It's based off of polarizability because it is more polarizable. That just means it's bigger, its valence electrons are further away from the nucleus, and thus it is able to distort its electron cloud more in order to perform an SN2 reaction. So iodide is a stronger nucleophile than chloride. All right,